YouTube viewers. In this video, what we're going to talk about is distributions used for hypothesis testing. And you can use just about any distribution for hypothesis testing, but I can't cover every single distribution in this course because if I did, it would be really long instead of long. But what distribution we're going to cover in this video is going to be the normal distribution, which is sometimes called a Gaussian distribution, a bell curve, or even a z-distribution. So we're going to give you a practice question to help you understand how to use the normal distribution in our hypothesis testing. So we're going to test whether the mean test score of students in a school differs from the national average when the sample size is large, and that means the sample size is greater than 30. So we're going to answer this question by writing a program in Python to do it, and we're going to import 3 libraries to answer that question. So we're going to import NumPy as NP, which is a numeric library, and we're going to import matplotlib.pyplot as PLT, which is a visualization library, and we're going to import scipy.stats and import norm, which is the normal distribution, and stats is the statistical module of the SciPy library, and SciPy is a scientific library. So after we have imported our libraries, what we're going to do is we're going to define our variables. So sample mean is 78, so that's the mean test score of the school. The national mean is 75, so that's the mean test score of the population. Sample standard deviation is 10, and sample size is 50, because the sample size has to be greater than 30. So now what we're going to do is we're going to set up our hypothesis. So the null hypothesis, H0, means the mean test score of the school is equal to the national average of 75. And the alternate hypothesis, H1 or HA, means that the mean test score of the school is not equal to the national average of 75. So now what we're going to do is we're going to calculate our standard error. So standard error equals the sample standard deviation divided by the square root of the sample size. So we're going to calculate our z-statistic. So the z-statistic is the sample mean minus the national mean, which is 3, divided by the standard error. And that's your z-statistic. Now we're going to calculate our p-value on a two-tailed test. So p-value equals 2 times brackets 1 minus norm.cdf, and CDF stands for cumulative distribution function, brackets ABS, that stands for absolute value, brackets z-statistic. So now we're going to calculate the z-value for a 95% confidence level. Z-critical equals norm.ppf, and I think that's percentage point function. Brackets, it's 0.975, because 0.975 is half of a two-tailed, half of 5%, and then half of 5% is the two-tailed test. So we're going to determine if we're going to reject the null hypothesis. Reject null equals ABS. Z-statistic is greater than Z-critical. So if the absolute value of Z-statistic is greater than Z-critical, then you're going to reject the null hypothesis. So we're going to print the results of the z-statistic, the p-value, and the decision whether or not to reject the null hypothesis. So Z statistic is 2.12, p-value is 0.339, and so basically the p-value is less than the significance level of 0.05, and since it's less than the significance level of 0.05, then what you have to do is you have to reject the null hypothesis and accept the alternate hypothesis. So that means that the national average is not the same as the sample. But of course, we already knew that because the national average is 75 and the sample average is 78. So the sample average is 3 points higher than the national average. So now what we're going to do is we're going to visualize our data. So we're going to visualize the normal distribution with critical regions. So x equals np dot line space brackets -4, 4, 1000, and that's going to set up your z-scores. And y equals norm.pdf, that's probability density function, brackets x, 0, 1, and that's your standard normal deviation. So we're going to plot the figure on a graph. So plt.figure brackets fig size equals 6, 4, and plt.plot brackets x, y, color equals blue, label equals standard normal deviation. And then we're going to shade the critical regions. So plt.fill between brackets x, y, 0, where x is less than negative z critical, and or x is greater than z critical, color equals red, alpha equals 0.3, label equals critical region. And so now we add our vertical lines to the z statistic and the critical z values. So plt.ax fig line brackets z statistic, color equals purple, line style equals dashed, line width equals 1.5, label equals z statistic. Then you have plt.ax fig line brackets neg z critical, color equals green, line style equals dashed, line width equals 1.5, label equals negative z critical. Then you have plt.ax fig line brackets z critical, color equals green, line style equals dashed, line width equals 1.5, label equals plus z critical. Now we're going to add labels, titles, and legends to the graph. So plt.title is a two-tailed z-test for mean test scores. The x label is z-score. The y label is probability density. And you get a legend and you get a grid as well. So we're going to show it. So you can see on the two-tailed z-test for mean test scores, you can see that the blue line is your normal curve that you have created. The pink line is the critical region. So we've got the purple line is the z statistic of 2.12, and the green line is the negative z statistic of neg 1.96, and you have another green line of the positive z statistic of 1.96. So you can see that the z statistic is in the critical region and it's past the z critical. And since the z-statistic is in the critical region, that means that it does not fall within the confidence interval of the mean. And the only thing that we're checking here is the critical region. We didn't actually check the confidence intervals, but you can see that the confidence interval is between the two green dashed lines, between the negative 1.96 and positive 1.96. And the z-statistic is 2.12, which means the z-statistic falls within the critical region, so the null hypothesis cannot be accepted. So that concludes this video. In the next video, we're going to be talking about the t-distribution, so I hope you decide to watch it.